Can you see the screen?
Not
Did I
yet.
share the screen?
No, sir.
No?
No, sir. I can see it.
I
Yes, sir.
think
Now
it
I can
should
see
now.
it.
Okay, so today we are going to start from the atomic models. Okay, so
Hmm.
far আমরা কি করেছি? So far we have done the discovery of electron, proton, neutrons, right?
Hmm.
From cathode ray, anode ray, the discovery of neutron from the alpha particle bombardment on beryllium sheet. এগুলো করেছি কিভাবে
Yes.
ইলেকট্রন প্রোটন নিউট্রন ডিসকভার হয়েছে, রাইট? অ্যান্ড দেন we have built it up by learning the properties of charge. তাই তো অ্যাটমের ভেতরে নিউক্লিয়াস আছে which is positively charged, electrons আছে which are negatively charged. তো অ্যাটমিক
Hmm.
মডেলস মানে কি? অ্যাটমিক মডেলস মানে যে অ্যাটমের ভেতরে এই সাব অ্যাটমিক পার্টিকেলস গুলো কিভাবে অ্যারেঞ্জ হয়ে রয়েছে, দ্যাট ইজ হোয়াট উই আর গোয়িং টু লার্ন। কিভাবে অ্যারেঞ্জ হয়ে রয়েছে অ্যান্ড কিভাবে দ্যাট উইল ইম্পার্ট স্টেবিলিটি, তাই তো? অ্যারেঞ্জমেন্ট অ্যান্ড
Hmm.
স্টেবিলিটি অ্যাটমে, এটাই আমরা পড়বো ইন ডিফারেন্ট অ্যাটমিক মডেলস। তো সেইটা বোঝার জন্য আমাদের কি জানা দরকার ছিল? দ্য প্রপার্টিজ অফ চার্জ which we have learned in the second lecture. So today we are going to start atomic models. Can you name the first model uh, we know about atom?
Boy's atomic model.
No, Bohr is not the first atomic model. So there
Rutherford.
is Rutherford is okay. Rutherford is first significant atomic
Thomson.
model, right? Thomson. The first atomic model is Thomson's model. Do you know anything about this?
Yes, sir. It is referenced as plum pudding model or watermelon model, and this is because he represented that entire atom. It is made up of positive charge, most of it, and the electrons were just randomly embedded into the positive charge, and they were
Right, so
scattered
that is
throughout it.
all about plum pudding model where we are considering, or Thomson who considered atom as a like watermelon, right? So the red part
Hmm.
of watermelon is like the uniform sphere of positive charge. Okay, একটা
Yes.
ওয়াটারমেলনের যে রেড পার্টটা থাকে সেটাকে একটা ইউনিফর্ম স্ফিয়ার অফ পজিটিভ চার্জ ধরা হলো, আর যে সিডস গুলো থাকে, রাইট, সো
Hmm.
দোজ আর কনসিডার্ড টু বি এমবেডেড ইনটু দ্য স্ফিয়ার অফ পজিটিভ চার্জ, মানে পজিটিভ চার্জের স্ফিয়ারের মধ্যে ইলেকট্রনস গুলো এমবেডেড হয়ে রয়েছে, বসে রয়েছে,
Hmm.
তাই তো? অ্যান্ড দ্য নাম্বার অফ ইলেকট্রন শুড বি সেম অ্যাজ নাম্বার অফ protons or positive charge.
Yes.
That makes the atom neutral. So that is simply Thomson's model. ठीक है जी? But the point is there is no significance of this model. This model cannot explain anything about atom, right?
Okay.
So basically, so we'll just read it like a history that Thomson was famous for electron discovery. So he gave this model. So we just learned the briefing, and now since we know that this has no significance, we are moving to the next model, which is the first significant model of atom. So can you name the model?
Uh, First
You already
one.
told me the name, so I'm just
Rutherford.
asking. Rutherford's atomic model, right? That was the first
Yes, sir.
significant model or significant atomic model. So
Hmm.
you will ask, why first significant atomic model? Rutherford model তো ভুলই বেরিয়েছে না? It is also proved to be wrong.
Hmm.
Then why I'm calling it the first significant model? It is because রাদারফোর্ডের মডেলটা হচ্ছে it laid the foundation, এর উপর বেস করে বাকি মডেলস গুলো ডেভেলপ করেছে, গ্র্যাজুয়ালি চেঞ্জ হতে হতে, রাইট? We now learn quantum mechanical model and others. Okay, so that is why
Okay.
Rutherford's atomic model is very important and we are going to learn this. So do you know the famous experiment of Rutherford?
Alpha scattering, the gold foil
Alpha
experiment.
scattering experiment, or it can be also called gold foil experiment. Alpha scattering experiment or gold foil experiment, right?
Hmm.
So this is the setup of gold foil experiment. মানে বাংলায় বলে সোনার পাত পরীক্ষা বা যাই হোক, so I am just mentioning the terms so that all the students can go through this and try to understand. So what is Rutherford's gold foil experiment? So first I'll explain the setup, right? So you can see this is a source of alpha particles. আমি আগে বলেছি alpha particle কি? Alpha particle মানে
helium.
ডাইপজিটিভ হিলিয়াম আয়ন, যেটা কোনো না কোনো রেডিওঅ্যাক্টিভ অ্যাটম থেকে বেরিয়ে আসে, রাইট?
Hmm.
So we have a source of alpha particles. This is a radium, radioactive, and the alpha particles are coming out of it. Okay, so this alpha particles are projected on a gold foil. এটা একটা গোল্ড ফয়েল, ঠিক আছে, যার উপর আলফা পার্টিকেলস গুলোকে কনসেন্ট্রেটেড ম্যানারে প্রজেক্ট করা হয়েছে, রাইট?
Hmm.
অ্যান্ড গোল্ড ফয়েলের চারিদিকে কি আছে? দিস ইজ এ মুভেবল স্ক্রিন কোটেড উইথ জিঙ্ক সালফাইড। ওকে, এ মুভেবল স্ক্রিন কোটেড উইথ জিঙ্ক সালফাইড। তো জিঙ্ক সালফাইডের ফাংশন আমরা আগেই বলেছি, রাইট? হোয়াট ইজ দ্য ফাংশন অফ জিঙ্ক
Phosphorescence.
সালফাইড? When it is
Pho-
excited or energized, it will give a greenish glow, তাই তো?
Hmm.
Chalo, so this is the setup. A source of alpha particle, and the alpha particles are projected on a gold foil of certain thickness. মানে gold foilটা না খুব বেশি thick হওয়া যাবে না, it has to be such so that the alpha particles can penetrate through it, তাই তো? মানে alpha
Okay.
particles গুলো যাতে এটাকে penetrate করে যেতে পারে, it should be such thick or such thin. Okay, and there is movable screen coated with zinc sulfide coating. This is the whole setup, and now we are going to learn the observations. Kiki observation holo? I think you know these things. Let me tell you. The first observation, as you can see here, the first observation হচ্ছে almost 99% of alpha particles are penetrating through the gold foil without any deflection. Okay,
Hmm.
so this is your first observation. Almost 99% of alpha particles যেগুলো straight gold foil penetrate করে বেরিয়ে যাচ্ছে without any deflection, মানে কোনো এদিক ওদিক হচ্ছে না, right? তো let's say
Yes.
theta is the angle of deflection. তো এদের ক্ষেত্রে theta কত হবে? 0 degree.
0.
That is the first observation. What is the second observation? যে খুব অল্প particles বা very small number of particles যাদের ক্ষেত্রে theta is not 0 degree, right? খুব
Hmm.
small
Small
angle
angle.
এরা deflect করে, they are deflecting in very small angles, right? And we can also say that if the theta increases, যদি angle of deflection যত বাড়ছে, number of alpha particles deflecting into that angle is decreasing,
Decrease.
তাই তো? মানে
Hmm.
let's say 15 ডিগ্রিতে যদি 30 alpha particles deflect করে, 30 ডিগ্রিতে 15 alpha particles will deflect, right?
Okay.
I hope it is understood.
Yes, sir.
That is the second observation. Now, what is the third observation here? The third observation is that all very rare, almost one in every 20,000 alpha particle. Okay, so they are bouncing back into the same path where they are projected on the gold foil. মানে যে রাস্তায় গোল্ড ফয়েলে হিট করছিল ঠিক সেম রাস্তায় দে আর বাউন্সিং ব্যাক, ঠিক আছে? মানে এখানে অ্যাঙ্গেল অফ ডিফ্লেকশন কত হচ্ছে? 180 ডিগ্রি।
Hmm.
These are the three observations which has been made. I hope it is clear.
Yes, sir.
Right. Now, can you tell me that what can we conclude or infer from this observation? এখান থেকে আমরা কি কি বলতে পারি?
Most of the space inside an atom is composed of empty space, which is why most of the alpha particles pass through without any sort of deflection. Then we can also say that since some positively charged alpha particles were deflected, then then the positive charge is not spread out throughout the atom, and it is concentrated in a small area. And we, after research, we could assume it was at the center, which is known as nucleus, as it is made of
Right.
positive
So,
charge and positive repulsion.
okay, let me explain all the points. You are more or less correct. So let me just make it quick. So these are the observation which I have already told you, right? One, two, three observations. So let me explain this. You are correct. The first conclusion is atom is mostly empty space, তাই তো? অ্যাটম পুরোটাই প্রায় খালি, কেন? বিকজ অলমোস্ট 99% আলফা পার্টিকেল উইদাউট ডিফ্লেকশন গোল্ড ফয়েল পেনিট্রেট করে বেরিয়ে যাচ্ছে। নাও গোল্ড ফয়েল ইজ মেড অফ লার্জ নাম্বার অফ গোল্ড অ্যাটমস।
Yes.
So since 99% alpha particles without deflection penetrate করছে, that means atom is mostly empty space.
Yes.
So that justifies the first observation. Now still we have two observation to justify. Second observation is what? There are very small number of alpha particles reflecting in small angles. তাহলে এই রিফ্লেকশনটা কেন হচ্ছে? Just tell me one thing. Alpha particle হচ্ছে dipositive helium ion, right? That means it is positively
Yes.
charged particle. So can you tell me একটা পজিটিভ চার্জ পার্টিকেল কে রিফ্লেক্ট করতে পারবে? আর এক পজিটিভ চার্জ পার্টিকেল নর এনি নেগেটিভলি চার্জ
Positive.
পার্টিকেল, right? So positive charge, a positive charge can deflect another positive charge because of repulsion, right?
Yes.
Because if there is a negative charge, it will not deflect, it will call upon. Not negative charge positive charge কে আরো নিজের দিকে টেনে নেবে, it will not deflect,
Hmm.
right? So that means what can I say? That অ্যাটমের ভেতরে পজিটিভ চার্জ আছে and that occupies a very small space of atom, right?
Yes.
And also third point হচ্ছে দেখ alpha particle is comparatively heavier particle. যেমন ইলেকট্রনের মাস নেগলিজিবল হয়, তো আলফা পার্টিকেল
Hmm.
ইজ কম্পারেটিভলি হেভিয়ার পার্টিকেল. নাও জাস্ট আই উইল গিভ ইউ অ্যান অ্যানালজি. লেটস সে there is a collision between a football and a table tennis ball, right?
Hmm.
So will there be deflection of football?
No, not significant.
Right, because the table tennis ball cannot deflect the football. যদি এটা ফুটবলকে ডিফ্লেক্ট করতে হয়, we need a comparable mass, যার মাসটা ফুটবলের সমান হবে বা তার থেকে বেশি হবে, right?
Hmm.
So what can I say here? We can say that that means the alpha particle is deflected by some comparable mass only,
Yes.
right? তাহলে এই যে second observation বা third observation where the deflection takes place, that can be justified by saying যে অ্যাটমের প্রায় পুরো মাস, almost complete mass of atom is centered at very small or concentrated at very small space, which also have the positive charge, right?
Yes.
Okay, so from here Rutherford also concluded his model. Okay, please try to understand properly. So these are all the points I just told you, right? So alpha particle that pass somewhat close to the nucleus experience a repulsive Coulomb force from the concentrated positive charge.
Hmm.
ठीक
Yes,
है?
sir.
Now third question, that which alpha particle will bounce back? Okay.
The ones that make contact with nucleus.
Okay. So let me explain with another diagram. So let's say this diagram. Can you see this diagram?
Yes, sir.
So you see it here. The alpha. So this is basically a central region of atom, very small region where we have positive charge. Also, the mass of atom is concentrated at this region. Okay, the central region, very small space, which almost carries all the mass of atom as well as the positive charge. Okay, now you can see the alpha particles which are passing away from the nucleus, passing far away from the nucleus, they will not deflect, there will be no deflection. You can see these ones, right?
Hmm.
But the particles which will come very close to the nucleus, they will experience repulsion and there will be deflection. Okay, and you can see more closer they come, greater will be the deflection, right?
Yes.
So you can see this particle, there is a deflection, but if you look at this particle, the deflection will be more. So let's say another particle come here, the deflection will be more. Okay, যত কাছে আসবে তত বেশি ডিফ্লেকশন হবে, রাইট? So 99%
Yes.
of alpha particles নিউক্লিয়াসের অনেক দূর দিয়ে চলে যাচ্ছে, so there will be no deflection. খুব small particles, they will come close, there will be deflection. But the alpha particle which is coming straight to the nucleus, okay, which is coming straight to the nucleus, now what will happen? As it as it
It will get deflected 180 degrees
No,
back
as it
to the
approaches
original.
to the nucleus, it will experience more repulsion, তাই
Hmm.
যত রিপালশন হবে তত স্লো ডাউন করতে থাকবে and kinetic energy will keep reducing. At some point
Hmm.
it will stop because it cannot move ahead, overcoming the repulsion, and from this point it will simply bounce back to the same path. So theta will be 180 degree. Okay,
Yes.
and this is the alpha particle which will come closest to the nucleus. Out of all the alpha particles, the alpha particle which is coming straight to the nucleus, as you can see here, it will gradually slow down. At some point it will stop and then it will turn back. Okay,
Okay.
and the point of turning back, the distance of this point from the nucleus is the closest distance of any alpha particle from nucleus. Is it clear? No other alpha particle can come this close.
Okay. So 180, when it is turned back
Right, the
180,
alpha
that is the
particles which
closest.
are deflecting in 180, right, they are
Hmm.
coming closest to the nucleus, and the closest distance will correspond to that point from where they are turning back.
Got it.
Is it clear? So all these justifications are given. All three observations are justified now.
Yes, sir.
So that led to the Rutherford's atomic model. Okay. So I'll just quickly brief the Rutherford's atomic model. What is happening here? So Rutherford, what did Rutherford say, or what was the atomic model of Rutherford? He simply said that entire positive charge, what is there? The entire positive charge and nearly all the mass of the atom is concentrated in an extremely small central region called nucleus. First point. And there are electrons occupy the space around the nucleus, right? And they are
Yes.
revolving around the nucleus in circular paths. So there is nucleus and there is extra nuclear region. Okay,
Hmm.
there is nucleus and there is extra nuclear region. Okay, so
What is the
nucleus,
extra nuclear region?
I mean the portion outside the nucleus, the remaining portion of
Oh,
the atom, that is called extra
okay.
nuclear region, where the electrons are revolving around the nucleus in circular paths.
Got it.
So we have electrons in circular paths in the extranuclear region. In nucleus, what we have? It has the mass of atom, right? It has positive charge. Okay.
Hmm.
Now Rutherford told what? The number of electrons should be same as number of protons in the nucleus, right?
Yes.
Which explains the neutrality of the atom. Number of protons and electrons must be same. So in nucleus, we have protons. But the point is, the mass of protons does not account for the complete mass of atom. An atoমের যে পুরো mass, that is not completely accounted by the protons. There is still some deficit of mass, right? Do you get me or not? Adit, am I audible to you? Can you hear me?
Yes, sir. Now I can hear you.
So what I am saying is that protons does not account for the complete mass of nucleus. There is some deficit of mass, right? So কি
Hmm.
হলো? Then he explained, okay, so there must be some other particles which also carry some mass, which is also present in the nucleus and which must be neutral because electron proton are already making the atom neutral. So the other particles which accounts for the remaining mass of atom should be neutral, and that is where neutrons are also having coming into the nucleus, right? So there are protons and neutrons. বুঝাতে পারলাম?
Yes, sir.
Since the protons অ্যাটমের পুরো মাসকে জাস্টিফাই করছে না, so the remaining mass is justified by some other particle যারা neutral, and those are neutrons. তাহলে নিউক্লিয়াসে কি আছে? Protons and neutrons. So this is Rutherford's atomic model. So there's lots of noise from your side.
Sorry, I was moving the chair.
So I hope it is clear, right? So far.
Yes.
But the point is, an atomic model is not only about the arrangement of the subatomic particles. It is also that model should justify the stability of the atom. Okay.
Okay.
So how Rutherford justified the stability of the atom? So he said, what does he say? He said simply that, let's say this is nucleus. Let's say the atomic number of the atom is Z. That means nucleus is Z khana proton আছে, তাই তো?
Hmm.
Right? Each proton
Yes, sir.
carries 1 unit charge. তাহলে নিউক্লিয়াসের টোটাল চার্জ কত? প্লাস ZE. So Q1 is equal to ZE.
Hmm.
তাই তো? আর এখানে যে ইলেকট্রনটা আছে সার্কুলেটিং around the nucleus in this path, the electron charge হচ্ছে 1 unit charge, right? So the amount of charge
Hmm.
here is E only. So we have already discussed this, right? The unit of
Yes.
charge is symbolized
Yes.
by E. So
Hmm.
there are two charges, is nucleus Q1 is equal to ZE and Q2 is equal to E, right? Now Rutherford said, or even I think তুইও হয়তো জানবি, if you have মানে তুই কি giant wheel চড়েছিস, giant wheels or merry go round, this kind of things যেগুলো
হ্যাঁ, হ্যাঁ।
ঘোরে? So if you have already experienced that feeling, তো কি হবে যখন এই নাগরদোলা বা জায়ান্ট হুইল ঘোরে, what happens there? তো মনে হয় না যে বাইরের দিকে ছিটকে যাবি?
হুম।
That means there is some force operating on you, right?
Yes.
Acting away from the center, তাই তো? তো সেম জিনিসটা
হুম।
এখানে ইলেকট্রনের উপর। রাদারফোর্ড সেড যে ইলেকট্রনটা যেহেতু সার্কুলার মোশনে রয়েছে অ্যারাউন্ড দ্য নিউক্লিয়াস, তাহলে ইলেকট্রনের উপর বাইরের দিকে একটা ফোর্স কাজ করবে, রাইট, হুইচ ইজ কল্ড সেন্ট্রিফিউগাল ফোর্স। সেন্ট্রিফিউগাল ফোর্স যেটা নিউক্লিয়াস থেকে বাইরের দিকে কাজ করে বা সেন্টার থেকে বাইরের দিকে কাজ করে ইন এ সার্কুলার মোশন, রাইট? লেটস সে যদি ইলেকট্রনের মাস এম হয়, অ্যান্ড ইফ দিস ইজ দ্য লিনিয়ার ভেলোসিটি অফ ইলেকট্রন, লিনিয়ার ভেলোসিটি ডিরেকশন ইজ শোন বাই ড্রয়িং দ্য ট্যানজেন্ট অ্যাট দ্যাট পয়েন্ট, ঠিক আছে? এখানে ট্যানজেন্টের যে
ওকে।
ডিরেকশনটা হবে দ্যাট শুড বি দ্য ডিরেকশন অফ লিনিয়ার ভেলোসিটি। তাহলে মাস, ভেলোসিটি এগুলো হলো, ঠিক আছে? এবার দেখ, ইফ অনলি সেন্ট্রিফিউগাল ফোর্স অপারেটস তাহলে তো ইলেকট্রন বাইরে ছিটকে যাবে, রাইট?
হুম।
But that does not happen because there is a centripetal force also operating. Centripetal মানে which is acting towards the nucleus, right? এখানে সেটা কি? The centripetal force is the electrostatic force or the coulombic force, যেটা এই দুটো অপোজিট চার্জের মধ্যে কাজ করবে। So the nucleus will attract the electron towards itself, it will pull the electron towards itself by coulombic force. Is it clear?
Yes.
Right? Another force said at any moment of revolution of electron, these two forces will counterbalance each other, and that is why electrons will neither will be ejected from the orbit or it will not fall upon the nucleus. Is it clear?
Yes, sir.
Right. So here you can see this is a force balancing equation. We already know that if there are two charges separated by a distance r, what should be the coulombic force? So that is K. Q1 is JD, Q2 is E. So Q1, Q2 is JD square. We are using the modulus force মানে ফোর্সের এক্সপ্রেশন আগেও আমরা করেছি, লাস্ট ক্লাসে we have done this, right? And the distance is
Yes.
r, so this is the coulombic force, right? And the centrifugal force is mv square by r. We are not going to derive this expression right now because in physics you have a whole chapter called circular motion where you can know these things, how these things are coming, right? So these are the force balancing equation given by Rutherford which should explain the stability of the atom. Okay, that is Rutherford's atomic model for you. He told you the
Uh,
arrangement of inside the atom, also explain the stability, and also
hmm.
we are going to learn what is the data obtained from Rutherford's atomic model, right? What is the helpful data or significant data which is obtained from Rutherford's atomic model? Okay, what do you think? Do you enjoy the class?
Yes, sir.
Okay, so these are the quantitative data from Rutherford's atomic model. So first data is he compared the radius of atom versus radius of nucleus. So he found that if the radius of nucleus is radius of atom is in the range of 10 to the power minus 10 meter, the radius of nucleus was found to be in the range of 10 to the power minus 15 meter. Okay, these are the data obtained by Rutherford. Okay, now we are not going to understand that how he measured these things. We are not going into that. But if you look at this ratio of radius of atom is to radius of nucleus, it is coming 10 to the power 5, right? What does that mean? That radius of atom is almost 10 to the power 5 or 1 lakh times greater with respect to radius of nucleus. Do you agree or not?
Yes, sir.
Okay, so it can reflect in the volume as well. If I compare the if I take the ratio of the volume of atom is to nucleus. Now, how do you calculate volume? Both nucleus and atom are considered to be sphere. Okay, and what is the volume of sphere? I hope you know that volume of
4
sphere
by 3 pi
4
r
by
cube.
3 pi r cube, right? The volume of a sphere is 4 by 3 pi r cube. Okay, so technically when I take the ratio of volume for atom and nucleus, the 4 by 3 pi that will be cancelled out. It should be nothing but the ratio of radius to the power 3, right?
Yes.
So that means 10 to the power 5 to the power 3 is 10 to the power 15. Okay, so
Okay.
what does that mean? That means atomic volume 10 to the power 15 times that of volume of nucleus. It is like if you go to a third desert and if you are trying to find a pin, তাই তো মানে
Hmm.
মানে থার্ড মরুভূমিতে যদি একটা তুই পিন খুঁজতে যাস, it will feel like that. I hope it is clear.
Yes, sir.
Okay, let us move to the next data or next result we have found from Rutherford's. So he also gave us the formula of nuclear radius. Okay, and the formula which is given by Rutherford is that if r is the radius of nucleus, let's say this is the radius of nucleus, as you can see, this
Hmm.
is radius of nucleus. This is a constant. The value of this is 4 by 3 into 10 to the power minus 15 meter. And
Yes.
E is nothing but the mass number of the atom. Okay. So you can use this
Okay.
formula to find the radius of the nucleus. Okay. So I'll
Okay.
give you a
What
quick
is R
problem.
zero?
Hmm?
What is R naught?
R naught is a constant.
Does it have any value?
Sorry.
Like, so do I have to substitute value of R naught?
Yeah, the value of R naught is 4 by 3 into 10 to the power minus 15. That is a constant.
Okay.
So can you try this one? This is a quick problem. You can just do it in your brain, mind, and
Okay.
tell me quickly.
So it will be 4 into 10 to the power minus 15 meter.
Right. So here you can see what is the mass number here?
27.
27. So you have A, 27 to the power 1/3 is 3, and R naught is. I think you can do this easily. So I
Yes,
am
sir.
not going into that. So let us move to the next data, which is obtained from Rutherford's atomic model. Right. And this is the Rutherford scattering formula. Now, what does that mean? Now, I tell you that in the gold foil experiment, theta যত বাড়বে, let's say theta is the deflection angle, right? তো theta যত বাড়ে, n theta তত কমে. So theta is the angle of deflection and n theta is the number of alpha particles deflected in that angle, right?
So can you write that down below that? What theta and n theta represents,
Theta
please?
is angle of deflection. I have already read that during the experiment, right?
Okay.
And let's say n theta is the number of alpha particles deflecting in theta angle. Is it clear to you?
Yes, sir.
Okay. So this is a qualitative relation that if theta increases, n theta will decrease. I'll give you the mathematical relation, and that is n theta is inversely proportional to sine to theta by 2 whole to the power 4. That is the mathematical relation
Okay,
between theta
so
and
I
n theta.
okay.
Okay. So I'll give you an problem again. You have to do it quickly. This is the problem. So can you read the problem quickly?
Yes, sir. Number of alpha particles
Not,
scattered
I
at
mean,
an
so that everyone can hear. This is going to record.
okay.
Yeah, read it quickly. Adit, are you there?
Yes, I'm trying.
So can you
So
just read it? Yeah.
1 by sine to the power 4.
Okay, let me read the question. I asked you to read the question, you did not. The question is if number of alpha particles scattered at an angle of 60 degree are 112 per minute. That means when theta is 60 degree, in theta is 112 per minute, right?
Yes.
You have to find the number of alpha particles scattering at an angle of 90 degree. So when theta is equal to 90 degree, you have to find, so this is n 60 degree. You have to find n 90 degree. That is what you need to find, right? Adit,
So I can just substitute the value.
right? So let us say this is equal to x. That is what I need to find, right? Now what do
Okay.
you see here? Now what do you see here? Can I say that in 60, what is the value of so here when theta is equal to 60 degrees, sine theta by 2 is sine 30, right?
Yes.
So can I write that in this case I want to find x, so I'll simply take the ratio of n90 by n60, right?
Oh, okay.
So this is nothing but x by 112, right?
Yes.
Okay. Now I want to take the, since I have taken the ratio, so what do you see? The denominator, they're inverse, right? So what
Hmm.
will be the denominator when theta is equal to 90 degree? It should be sine 45,
Yes.
right? So it will come down because 90 is at up. Do you agree?
Yes, sir.
And for 60 degree, what should be the theta by 2? It is 30 degree.
30.
Since they are inverse, it will go up. So it is sine 4, sine to the power 4, 30 degree. Now you just need to calculate this to find x. So I'll leave it to you. I am not going to the final calculation. I have put everything in the equation, how to solve. So I have told you the process or the approach. I hope you understood, right?
Yes.
Okay. So let us move to the next part, which is how to find distance of closest approach. Okay. So this is the type of question once came into the IIT question. So long before, right? So, but let us give it a shot. Can you see this?
Yes, sir.
Okay. Now let us look at the distance of closest approach. Okay, now I already told you which alpha particle will come closest to the nucleus. কোন alpha particle টা সব থেকে কাছে আসবে?
The one that is getting deflected by 180 degrees.
Right, so it will bounce back at 180 degrees. So let's say this is nucleus. This is the nucleus of gold atom, right? Which is considered as a
Okay.
sphere. Okay, this is the
Yes.
nucleus of gold atom, which is considered as a sphere. The atomic number of gold is 79. That means the charge of this nucleus is 79 unit charge, which is 79 E, right?
Yes.
Okay, fine. Now let's say this is the alpha particle which is projected straight to the nucleus. Let's say this is point A, and at this point velocity is VA. I hope I am making things clear. So from
Yes.
point A, the alpha particle is projected straight towards the nucleus, right? Alpha particle means di-positive helium ion. As you can see, the charge of helium ion is 2 unit. So Q2 is equal to 2 unit, Q1 is equal to 79 unit, 79 E and 2 E. So from at point A, the alpha particle is projected with a velocity of VA, right? Is it okay?
VA.
So let's say the point A is at infinite distance from nucleus initially at this stage. Why? Because at this distance the nucleus has no influence over the alpha particle. Okay, that means
Okay.
it is beyond the range of electric field of gold nucleus, right?
Yes.
Okay. Now say let's say from this point the alpha particle comes under the influence of nucleus. That means from this point we are considering it a finite distance. Is it clear to you?
Yes, sir.
এখান থেকে আমরা একটা ফাইনাইট বা নির্দিষ্ট ডিস্টেন্স ধরে নেব। এখানে আমরা
Hmm.
ইনফাইনাইট ডিস্টেন্স ধরছিলাম কারণ এখানে নিউক্লিয়াসের কোনো ইনফ্লুয়েন্স ছিল না, এখান থেকে ইনফ্লুয়েন্স স্টার্ট হলো। তো ক্যান আই সে ফ্রম দিস পয়েন্ট আলফা পার্টিকেল উইল এক্সপেরিয়েন্স রিপালশন অফ নিউক্লিয়াস,
Yes.
তাই তো? তাহলে এখান থেকে ও আস্তে আস্তে স্লো ডাউন করবে,
Hmm.
স্লো ডাউন করতে থাকবে, মানে কি হবে, কাইনেটিক এনার্জি অফ আলফা পার্টিকেল কি হবে, কমতে থাকবে। It
Yes.
will start reducing from this point, তাহলে কমতে 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 there will be a certain point যেখানে এসে ও থেমে যাবে, it will stop, velocity zero হয়ে যাবে, kinetic energy zero হয়ে যাবে। let's say this is point B, right? so at this point যত কাছে আসছে তত কি হচ্ছে, রিপালশন বাড়ছে তো।
Hmm.
সো মানে গ্র্যাজুয়ালি রিপালশন বাড়ছে, কাইনেটিক এনার্জি কমছে, at this point the repulsion will stop the particle B, and from this point the alpha particle will return back. So this is the point of returning, and let's say this point is B, and the distance of nucleus from point B can be called closest distance of approach. Is it clear?
Yes, sir.
Okay, so let's say this distance of closest approach is R naught. Okay,
Hmm.
this is R naught, that is the distance of closest approach, and that is what you need to find. Okay, so how do I do this? Please try to understand. You know that energy of the alpha particle should be conserved because if the kinetic energy is reducing, potential energy should increase.
Yes.
The total energy must be conserved. So can I use that principle that the total energy at point A should be same as the total energy at point B?
Yes.
Okay, so at this point A, kinetic energy at point A is half of m alpha Va square. M alpha is the mass of alpha particle, right?
Is there some? How did we get this formula?
You don't know the formula of kinetic energy, which is
Oh,
half,
okay. Half mv
half
square.
mv square.
Yes. Yes. Yes.
So this is half m alpha Va square. Va is the velocity at point A. M alpha is the mass of alpha particle, which is nothing but 4 amu, right?
VA is velocity of alpha particle, right?
Va is velocity of alpha particle at point A,
Okay.
right? M alpha is the mass of alpha particle, which is 4 amu. I hope you know now what is amu and how to convert it into gram, right? You know these things.
Yes, sir. Yes, sir.
Okay, so this is the kinetic energy at point A. I think you also know the expression of potential energy. Let's say there are two charges Q1, Q2 separated by a distance R. So this must be the potential energy,
Hmm.
right? And at point A, the distance from nucleus is infinite, right? So if R is equal to infinite, If this is equal to infinite, can I say that potential energy at point A is 0?
Yes.
Okay, so we have found the kinetic energy and potential energy at point A. I hope it is clear to you.
Yes.
Now at point B, kinetic energy is 0. Do you agree?
Yes.
But the potential energy should be K into Q1, Q2 by R naught, since here the distance is R naught, which is the distance of closest approach, right?
Hmm.
So what? Now total energy at point A should be equal to total energy at point B. So at point A it
Yes.
is half m alpha VA square. At point B it is K into Q1, Q2 by R naught. Now you can see in
Hmm.
this expression Q1, Q2 is known, right? You can also convert them into Coulomb if you want. K is also known. You know the value of K. Mass of
Yes.
alpha is known and VA will be given to you, right? Mass of
So
alpha
so
is known.
what? So what do I have to find then?
You need to find R naught, the distance of closest approach. The question mark is there, right?
Okay.
So everything is else is known or given. Q1, Q2 is known, mass of alpha is known, K value is known, it is a
K
constant.
value is 1 by 4 pi. Then
Right,
that
9
value.
into 10 to the power 9 Newton.
Okay.
So, right, that value. On CGS it is 1. So everything is known except R naught. When VA value will be given, this velocity will be given to you. Okay.
Okay.
So from here you can find the distance of closest approach R naught. Is it clear to you or not?
Yes, sir.
So is there any doubt?
No, sir.
So I think I'll give you a homework based on this problem. So you will do it at home and send me. I'm just putting the question in the lecture. So take it as homework and do it. Okay.
Okay, sir.
This is the homework. So everyone can try here. Okay. So we have got the results coming out of the Rutherford's atomic model as well. Right?
Yes.
Okay. Next, we'll move to the drawbacks of Rutherford's atomic model. Do you have any idea? Do you know anything about Rutherford's drawbacks of Rutherford's atomic model?
Yes, sir. The atomic instability. Then the it could not explain hydrogen spectra.
Right, but do you know what is hydrogen spectra?
Little bit. I know a little bit.
You know a little bit. Anyway, little bit is not sufficient. Okay, so let us understand the drawbacks of Rutherford's atomic model. Unless you know the drawbacks, you cannot move to the next model, right? Not only the
Okay.
drawbacks, you have to also understand new theories, which will be the building blocks of the new models. Right. The first drawback, which is very important, and that is violation of classical electromagnetism. Look, back then when Rutherford gave the model, electromagnetic wave theory was the backbone of the classical physics, right? And which is usually uh, almost everywhere. Okay. Now, as per Maxwell's electromagnetic theory, an accelerating charged particle must radiate energy as electromagnetic wave. Now, what does that mean? Let's say this is nucleus, okay,
Yes.
and this is a circular path where an electron is revolving around the nucleus. So let's say I have not drawn the circle properly. So let's say this is a circular orbit where an electron is revolving around the nucleus. This is the electron.
Hmm.
Okay. Now, as per Maxwell, when a charged particle is revolving around another charge, anyway, so this is an accelerating charged particle. This electron is an accelerating charged particle. So as per electromagnetic theory, it must radiate energy as electromagnetic wave. So it is radiating electromagnetic energy in form of waves. Okay, as per classical physics or as per Maxwell's theory. Now, if the electron continuously loses energy, this continuous loss of electromagnetic energy. তো কন্টিনিউয়াসলি ইলেকট্রোম্যাগনেটিক এনার্জি লুজ করছে। তো যদি
Hmm.
এনার্জি লুজ করে, so can I say it will be tired, and now what will happen? It will uh, basically it will surrender to the nucleus because the nucleus is pulling it back towards itself, right, by Coulombic force.
Yes.
তাই তো? তো ইলেকট্রন যদি কন্টিনিউয়াসলি এনার্জি লুজ করতে থাকে, তার মানে কি হবে? ও আস্তে আস্তে নিউক্লিয়াসের কাছে এগিয়ে যাবে,
And it will eventually collapse into the nucleus.
right? Now how will you do that? How will it do that? So কি হবে? Continuously the radius of the orbit will keep shrinking. As it continuously loses its energy, the radius of the orbit will continuously keep shrinking, and like this, in a spiral motion, the electron will fall upon the nucleus, right?
Hmm.
Around 10 to the power minus 8 seconds. So it does not take much of a time. So all the electrons will do the same and the atom will collapse. So that means the Rutherford's model cannot explain the stability of the atom. That is the first
Okay.
point. Okay, what are the other drawbacks of Rutherford's atomic model? So you can see it here. What do you see? Second point is it cannot explain the atomic spectra. You know that hydrogen is the simplest atom, right, out of all of them.
Yes.
So it does not even explain the atomic spectra of hydrogen atom. So that is a major failure. It cannot explain the simplest atom. We are not even
Hmm.
talking about the complex ones. It does not explain the behavior of the simplest atom. Now atomic spectra, what is spectra? What is atomic spectra? We are going to learn that later as we progress in the chapter. But think like that, যে simplest atomer behavior explain করতে পারছে না. That is a major drawback.
Yes.
Okay. Third is no explanation of allowed orbits. Rutherford just said that electrons will revolve around the nucleus in circular orbits. ঠিক আছে, কিন্তু he did not specify the circular paths. মানে এটা যে কোনো circular paths হতে পারে, random যে কোনো কিছু যার radius 0 to infinity anything হতে পারে as per Rutherford, right?
Hmm.
But later on it is found to be wrong. Bohr's model সেটাকে ঠিক করেছিল. Bohr specified those orbits where
Hmm.
the electrons are allowed to revolve around the nucleus. So that is a drawback. It did not specify those orbits, right?
Yes.
And also cannot predict the spectral frequency. Again, it goes back to the spectrum of hydrogen atom. These are basically the characteristics of hydrogen spectrum which cannot be explained by Rutherford's model. So these are the drawbacks.
Yes, sir.
Okay, so the next Rutherford's model is done here. So next, what we are going to do is, before moving into Bohr's atomic model, the next model, what we need to do is we need to understand the dual nature of energy. Dual nature, that is wave nature and particle nature, right? So that is the next topic we are going to learn in the next class, which should be tomorrow. আচ্ছা, tomorrow কালকে আমরা একটা কাজ করি, কালকে let us start from 10 or 10:30 am. Okay.
Okay, 10, 10 which one? 10 or 10:30, sir?